We've so far learned the product rule, which is for when we're multiplying two equations together. We've learned the quotient rule for when we're dividing two equations. Now we're going to learn what to do with composite functions. What do you do when you plug one function into another? This is called the chain rule. So you see here the general form. If g of x is plugged into f of x, then the derivative is f prime of g of x times g prime of x. So let's focus in on this rule for a second. If you just look at this piece first, we call that the derivative of the outside. So we take the derivative of the outside function, but if you notice, we leave the inside alone. It's still just g of x on the inside. So you take the derivative of the outside and leave the inside alone. Then, you look at this part, we multiply that by the derivative of just the inside. So the simple way to say this is derivative of the outside times the derivative of the inside. So one thing that's important to be able to do is not only be able to perform the chain rule, but to know when you have to use it. Now if you look at these two examples, 3 times sine of x and sine of 3 of x, one of these requires the chain rule and one does not. So I'm going to give you just a second to think about that. You can pause if you want longer. The correct answer is B. B requires the chain rule. The reason is, inside of sine, we've placed a 3x. So we're going to have to use the chain rule on that, and you'll see how in just a moment. But looking back at A, you don't need the chain rule because you can just take the derivative of sine, which is cosine, and just leave the 3 out front. Coefficients just stick around. There's nothing special or requiring the chain rule about that. Now some of you might say, well, wait a minute, x has been plugged in. Well, that's true. But if x is all that's on the inside, it doesn't really matter, because if you multiply by the derivative of x, you're just multiplying by 1, so you're not going to be changing anything. So I think as you see some examples, you'll see this is pretty straightforward. So let's start with this one. What's happened to this function is there was a 4x squared plus 3x plus 1, and it got plugged inside of an x to the 4th function. So my outside function is really x to the 4th. I've just plugged something else in for x. So I treat that power of 4 as my outside function. And I start by taking the derivative of the outside. So I multiply the 4 down and subtract 1 from the exponent. So again, you're just treating that inside part like a giant x right now. You're multiplying by the exponent, subtracting 1 from the exponent. So that's the first part. That's the derivative of the outside. Then you multiply that by the derivative of the inside. And that's it. The only thing left to do is just some simplifying. We can't really do anything with this piece because of the cubed, unless you want to cube the whole thing out, which I would not recommend. But the two pieces on the ends can be combined. So I do 4 times 8x plus 3. I get 32x plus 12 times 4x squared plus 3x plus 1 cubed. And that is your first chain rule problem. Derivative of the outside times the derivative of the inside. Okay, this next one, we had an x cubed plus 2x function, and it's been plugged into a square root. What I would recommend here, though, is to rewrite this. It's a lot easier to deal with this if you go ahead and change the square root to be a power of 1/2. So we take the derivative of the outside first, and this time our outside is that power. It's the 1/2. So we multiply by 1/2 and then subtract 1 from the exponent. That's the derivative of the outside. And then we multiply by the derivative of the inside. So we're multiplying by just the x cubed plus 2x. And then our last step is to just simplify. Multiply this piece times this piece, and we get 3/2 x squared plus 1 times x cubed plus 2x to the negative 1/2. Now just so you know, at least as far as I'm concerned, that answer is completely good, but it could be rewritten a couple ways, and I want to make sure you see how it's the same thing. This negative exponent means you could move that whole piece down to the bottom of a fraction. And if you recall, raising something to the 1/2 power is the same thing as raising it, as taking the square root of it. So if you're in my course, I really have no preference over any of these three forms. All three are good. But I just want to make sure you remember and you're aware and you're used to seeing all three, because particularly in multiple choice questions on the AP test or something like that, you could see it in any one of those forms. Okay, so now let's try this next one. We've got 1 over x plus 1. You could use the quotient rule on this, and from this point forward, if you would prefer to do that, that's fine. What allows you to do the chain rule here actually has to do with the numerator. The fact that the only thing in the numerator is a number, it doesn't have to be 1, it could have been 7 or -3 or any number, that's what's going to allow us to use chain rule. Most of the problems you're going to do quotient rule with have x's top and on the bottom. And in that case, you can't usually just convert to a chain rule problem. But this one we can, because it's just a number on top. Because if you look, x plus 1 to the first on the bottom can be rewritten as x plus 1 to the -1 on top. Now hopefully you can see how it's a chain rule problem. We've got an outside function, that's the -1. And then we multiply by the derivative of the inside, which is just 1. So really this is just -1, x plus 1 to the -2, or if you prefer, -1 over x plus 1 squared. Alright, this one we have on the bottom the cube root of x squared minus 1 squared. Again, we just have a 2 on top, so that's going to make it okay for us to bring it up and eventually use the chain rule. Well, the cube root of something squared is the same thing as raising it to the 2/3. And then we can move that up top by making it a -2/3. So now we multiply by the -2/3. Subtract 1 from the exponent, multiply by the derivative of the inside, which is 2x. Again, we can simplify by multiplying these two pieces together. We get -8 over 3x times x squared minus 1 to the -5/3. And you can leave the answer just like that, or if you prefer, you can move that x squared minus 1 to the -5/3 to the bottom to make it a +5/3. Okay, now we're going to switch gears a little bit and look at some trig. So let's start with sine of 3x. This is the one I had in the example earlier when we were comparing what needed it and what didn't. So again, it may be helpful to write parentheses there. That may help it make more sense to you. But in this case, sine is the outside function and 3x is the inside function. So we take the derivative of the outside function, the derivative of sine is cosine, but we leave the inside alone. We don't change it. It has to stay there, but we don't change it. So that's the derivative of the outside. Then we multiply by the derivative of the inside. The derivative of 3x is just 3. And you can technically leave it like that, but conventionally we usually move that 3 up front. And write that is our answer. Okay, next up we have secant of pi x. Again, it may help you if you write the parentheses around the pi x to show you that they are the inside and secant is your outside function. So when you take the derivative of the outside function, the derivative of secant is secant pi x times tangent pi x. Then you multiply by the derivative of the inside, which would just be pi. You can leave it like this, it's not incorrect, but most of the time what will happen is they will pull the pi out front. Now notice on this one, even though secant split into two different functions, secant and tangent put together, multiplied together, the inside part had to stay the same. The inside part had to be pi x still for both of them. Okay, now I want you to compare the two that you see on top there. Tangent of x squared and tangent squared x. So first of all, tangent of x squared really just means this. So this one is really similar to the first two we did. Tangent's on the outside, x squared's on the inside. However, g of x over here on the right hand side, tangent squared x, really means the same thing as this. Now I know you may be asking, well, why don't they write it that way? As far as I know, the only motivation is they didn't want to have to write parentheses. So they decided to put the squared there. But when the squared's written in between the tan and the x, you're not squaring just tan. That doesn't make any sense. You're not squaring just tangent by itself. You can't do that. You're squaring the whole thing. So if you look here at the left side, the f, our outside function is tangent, and our inside function is x squared. On the right-hand side, it's the opposite. Our outside function is the squared, and our inside function is the tangent. So let's do f of x over here on the left first. The derivative of the outside function, the tangent, is secant squared, and we leave the inside as x squared. Then we multiply by the derivative of the inside, which is 2x. So most of the time, they'll pull the 2x out front. Again, that's just kind of by convention. It's not mathematically necessary. And we'll get that as our answer. Now g, on the other hand, our outside function is that squared. So we multiply by the 2 and subtract 1 from the exponent. Then we multiply by the derivative of the inside. So we end up with something that looks pretty different. So just a subtle difference in where the exponent is makes a pretty big difference in what our answers are going to look like. Okay, if you look at this last example, I know it's been a long video, bear with me, thank you for being with me this far. This last example, we have 5 cosecant cubed of x squared minus 1. And I went ahead and took that cubed and put it where it's a little easier to understand what it's doing. Because it is cubing that entire cosecant, x squared minus 1. It's not cubing the 5, but it is cubing everything else. Now if you look closely at this function, they're actually not just an outside and inside piece, but an outside piece, a middle piece, and an inside piece. So there are 3 pieces. So I'm going to try to color code this so you can see what I'm talking about. We have the 5x cubed. We have the cosecant of x squared minus 1. And then we have x squared minus 1. So there's 3 layers here. So we actually kind of have to do a double chain rule. We start by taking the derivative of the outside of the 5 with the cubed. So I'm going to stick with my color blue. I multiply by the 3 and subtract 1 from the exponent. That's the derivative of the outermost piece. Then I come to the next piece as I work my way inside, and I come to the cosecant next. The derivative of cosecant is negative cosecant x squared minus 1 cotangent x squared minus 1. Then my last piece is the red piece, the x squared minus 1, and its derivative is simply 2x. So there's a little bit of simplifying I'd recommend you do here. We can pull the 2x, the negative, and the 15 all out front, combining them to get a negative 30x. We can also combine the cosecant of x squared minus 1 squared times the cosecant of x squared minus 1 to make it cosecant cubed of x squared minus 1. And if you'd rather put parentheses and put the cubed outside, that's completely fine. It means the same thing. And then lastly, we've got to bring down this piece, which is the cotangent of x squared minus 1. So be on the lookout for some trig ones and even some non-trig ones, because sometimes you may have 3 pieces, in which case you've got to do a double dose of the chain rule.